Let us look at first fundamental theorem of isomorphism. So we have a group G and a group H. Phi maps G to H by a homomorphism. Kernel of phi is always a normal subgroup of G, and image of phi is a subgroup of H. Then there exists a unique isomorphism psi which maps the quotient group G by kernel of phi to image of phi, such that psi of G times kernel of phi is equal to phi of G for all G in G. Now here we know that kernel of phi is a set of elements in G that maps to the identity of H, and image of phi is the set of elements phi of G which is a subset of H, or in other words the elements of H that actually gets mapped by phi. So the theorem says that G by kernel of phi, the quotient group, is isomorphic to image of phi. So pictorially this is what it would look like. So we have a group G, phi maps G to the image of phi is a subgroup of H. Then a isomorphism exists, say psi, which maps G by kernel of phi to the image of phi. So we have phi, we have psi. So we have to show that this mapping and this mapping are equivalent. Now that can be only equivalent if we compose psi with pi, so that we can say equivalently that phi is equal to the composition of psi and pi. Here assuming that pi is a mapping from G to the quotient group G by kernel of phi. So in simple terms, if we take the quotient group of G with the kernel of phi, what remains behaves like the image of phi in H. Phi maps G to H, but the theorem is about cosets in the quotient group G by kernel of phi. So we define a new map, psi, which maps G by kernel of phi to image of phi. Prove psi of G times kernel of phi is equal to phi of G. Okay, so let's make sure that it is well defined. To verify that it is well defined, we check whether phi of G1 is equal to phi of G2 if cosets formed by G1 and G2 with kernel of phi are equal. So we start with G1 times kernel of phi is equal to G2 times kernel of phi, the cosets. Then left multiplying by G inverse, we get G inverse times G2 is in kernel of phi. So G inverse times G1 becomes the identity. And on this side, we get G1 inverse times G2, so that we can say that G1 inverse times G2 is in kernel of phi, which implies that pi of G1 inverse times G2 is equal to the identity of H, which again implies that phi of G1 inverse times phi of G2 is equal to E of H. So that we get, since on this side we have EH, we bring this inverse to this side. So we end up with phi of G1 is equal to phi of G2. And hence psi is consistent. That is, it is well defined. Now let's check whether it is a homomorphism or not. For cosets G1 times kernel of phi and G2 kernel of phi, psi of the product of G1 kernel of phi times G2 kernel of phi This can be written as psi of G1 times G2 times kernel of phi. This will map to phi of G1 G2 is equal to phi of G1 times phi of G2. So psi of G1 kernel phi times psi of G2 kernel phi is equal to phi of G1 times phi of G2. Psi is a group homomorphism, we can say. Now let's look at surjectivity. By definition, every element of image of phi has the form phi of G for some G in the group G. And we have seen psi of G times kernel of phi is equal to phi of G. So which implies psi is surjective. Now we look at injectivity. The only way that psi of G times kernel of phi maps to the identity of H is if phi of G is equal to the identity of H. So, which we can write it as psi of G times kernel of phi is equal to identity of H if and only if G is in the kernel of phi. From where did this come? Because phi of G will be equal to E of H means that that particular G is in the kernel. Okay. So the kernel of psi is trivial. And we can say now that psi is a bijective homomorphism, that is an isomorphism, and G by kernel of phi is isomorphic to image of phi through the isomorphism psi. And how can we make this statement? Because we have shown that psi is well defined, psi is a homomorphism, psi is subjective, and we have shown that it is injective. Since psi is a isomorphism, that means G by kernel of phi gets mapped to the image of phi. Now here you might have noticed that we are not mentioning pi anywhere except here phi is equal to the composition of psi and pi, and in the diagram pi. That is because whenever we have a mapping between G and its quotient group with the kernel, that is G by kernel of phi, pi is understood to be there as a canonical projection. So this will always be there, and that is why it is not mentioned in any part of our workings. Now let's look at an example. Let's say we have a group G, which is the group Z12, that is the set of integers under addition modulo 12. And we have the image of phi, that is the set of integers addition modulo 4. And phi is the mapping between G and say H. Image of phi is a subgroup of H. So in other words, phi takes a number addition modulo 12 and then reduces it to addition modulo 4. Now here what will be the kernel of phi? Is a set of elements that maps to the identity of H. Now identity of H is what? Is 0 in the addition modulo this one. So what are those elements of Z sub 12 which maps to 0? And that is the congruence class 0 under addition modulo 12, congruence class 4, and congruence class 8. So kernel of phi is a subgroup of order 3. The quotient group formed by Z sub 12 with kernel of phi is equal to cosets of kernel of phi in Z12. So what are these cosets? We have these cosets. Congruence class 0 plus kernel of phi is equal to 0, 4 and 8. Congruence class 1 sub 12 plus kernel of phi is equal to 1, 5 and 9. Similarly for 2 and for 3 congruence classes. So that means in the set form, we can write it as Z sub 12 by kernel of phi is equal to 0 plus kernel of phi, 1 plus kernel of phi, 2 plus kernel of phi, and 3 plus kernel of phi. Image of phi is equal to Z4. So phi is on 2, which basically means that all the elements of image of phi are getting mapped by phi. So now we define psi, which maps the quotient group Z sub 12 by kernel of phi to the Z4. How? Through psi of the coset congruence class X sub 12 plus kernel of phi is equal to congruence class X sub 4. So what do we get? Psi of 0 plus kernel of phi is equal to 0. Psi of 1 plus kernel of phi equal to 1. Psi of 2 plus kernel of phi equal to 2. Psi of 3 plus kernel of phi equal to 3. So that we have Z sub 12 by kernel of phi is isomorphic to Z4. So we have, using an example, shown the first fundamental theorem of isomorphism. So again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.